Relaxed motoring is at the core of the Rover brand philosophy. With this in mind, the Rover 75 is offered with a choice of 4 new, powerful engines, which provide effortless performance and never seem stretched. The range comprises 3 petrol engines and 1 diesel, all employing the very latest technology. This programme features all 4 engines, together with their management systems, and is in 4 sections. Section 1 looks at some of the more general features relating to all engine variants. Section 2 covers the new 4-cylinder 2-litre diesel engine, known as the M47R. It utilises the revolutionary Bosch common rail direct injection system and develops 85 kilowatts of power. Section 3 is all about the 1.8-litre petrol engine. It's the familiar, though greatly updated, K1.8, which has been further developed to improve performance and now produces 88 kilowatts of power. And finally, Section 4 covers the 2 remaining petrol engines, which are both derivatives of the KV6. One has a capacity of 2 litres, developing 110 kilowatts, and the second version of 2.5 litres produces 130 kilowatts. The 2-litre version has been specifically designed for the Rover 75 and, apart from its capacity, is identical in construction to the 2.5-litre unit. The under-bonnet appearance of all models is pleasing and neat. Fluid reservoirs are clearly labelled, and those that may require attention by the owner are easily accessible. All engines are mounted transversely, and to minimise noise and vibration, a special twin tie-bar torque axis mounting system has been developed. This comprises a hydro mount on the right-hand side and a hydro bush on the left, that together support the engine assembly. Additionally, there are 2 tie bars to control the torque reactions of the engine during acceleration and deceleration. Engine cooling is provided by a radiator with an aluminium matrix and is a product of the latest heat exchanger technology. The vehicle's normal ram airflow is supplemented by an electric cooling fan that's the largest ever to be fitted to a Rover. It serves both the radiator and the air conditioning system's condenser. The cooling system is filled with a new type of corrosion-inhibiting coolant that is replaced every 4 years, but which has a potential service life of 100,000 miles. Oh, and by the way, both V6 engines and the diesel engine incorporate an engine oil cooler. All engines are coupled to either the new 5-speed manual or 5-speed automatic transmission. It's also the first time that an automatic gearbox has been offered for a diesel-powered Rover car. In line with the multi-valve petrol engines, the new diesel also incorporates 4 valves per cylinder, which means multi-valve engines operated by double overhead camshafts feature throughout the model range. As you might expect, all engines comply with the current environmental legislation. However, they will also meet the forthcoming year 2000 European regulations, known as ECD3, regarding the level of exhaust emissions, fuel evaporative emissions, and onboard diagnostics. ECD3 legislation requires engine management systems to monitor and record faults that directly affect emissions. The onboard diagnostics provides this function. When detected, ECD3 faults are recorded in the ECM's memory in the same way as any other fault. You can, of course, retrieve faults by interrogating the fault memory using testbook. As of January 2001, all vehicles fitted with petrol engines will be required to notify the driver of any serious faults by illuminating the malfunction indicator lamp, known as MIL for short. Rover 75 petrol engine management systems will have the malfunction indicator lamp active before this date. And during the first decade of the millennium, legislation governing the MIL lamp of diesel vehicles will be introduced. The M47R diesel engine is the latest addition to the new generation of diesel engines being developed jointly by Rover and BMW engineers. The 2-litre 4-cylinder engine is equipped with chain-driven double overhead camshafts and 4 valves per cylinder. It develops 85 kilowatts of power at 4,000 RPM and produces 260 Newton-meters of torque at a remarkably low 2,000 RPM. This torque is available across a wide range of engine speeds, making it incredibly flexible. The valves are operated by hydraulic valve adjusters via roller-type rockers, which help to make the engine extremely quiet. This arrangement also reduces friction and consequently enhances fuel efficiency. Other noise reduction measures include a separate aluminium 2-piece sump, a plastic cam cover with integrated air filter housing, and pilot fuel injection to reduce the characteristic diesel clatter. However, we'll look at the fuel injection system shortly. The diesel engine's coolant circuit also incorporates an auxiliary coolant heater fitted ahead of the heater matrix. If, when the engine is started, the ambient air temperature is below 5 degrees centigrade, the coolant heater will draw fuel from the tank and burn it. As a result, the coolant is heated, which accelerates the warm-up of both the engine and the passenger compartment. And because the engine reaches optimum operating temperature quickly, the auxiliary heater has a negligible effect on the overall fuel consumption. Incidentally, the cooling system's thermostat is located on the end face of the cylinder head. The engine ancillaries are driven by 2 poly-V belts. One drives the air conditioning compressor and is manually tensioned, whilst the other, which is automatically tensioned, drives the remaining ancillaries, such as the power steering pump, water pump and alternator. Note that the drive belt's service life is 90,000 miles or 6 years. A turbocharger and intercooler assist in filling the combustion chambers with a high volume of dense air. And this, together with the engine's 4 valves per cylinder and the highly efficient injection system, ensure optimum combustion performance. The engine is fitted with the revolutionary Bosch common rail direct injection system. It overcomes the disadvantages of previous injection systems, where the fuel pressure and the volume of fuel delivered varied with engine speed. Common rail technology is similar in approach to fuel injection systems fitted to petrol engines. A lift pump supplies fuel from the tank via a filter to a low-pressure pump and then onto a chain-driven high-pressure pump on the engine. Here the fuel is pressurized and then delivered to the rail, which in turn supplies the injectors. The rail also acts like an accumulator, providing a supply of pressurized fuel, whilst at the same time dampening any surges. Excess fuel is returned to the tank via a fuel cooler, which is situated next to the right-hand rear wheel. Typical fuel pressures in the rail are in the region of 1,350 bar, so extreme care must be taken when working on the system. Always refer to the repair information before attempting repairs. 4 solenoid-controlled injectors spray the fuel directly into each combustion chamber. Their firing time and opening duration is calculated by the ECM. Each injector is independently controlled and delivers a pre- and main injection quantity of fuel in quick succession per cycle. This introduces the fuel more gradually, thereby reducing the characteristic ignition delay associated with normal diesel injection systems. This feature, combined with the constant high pressure, results in smoother and more precisely controlled injection, which improves the burning of the mixture, reduces emissions, and improves performance. For the driver, it simply means an extremely refined engine. By the way, the exhaust gas recirculation valve is mounted on the inlet manifold, and unusually, like the manifold, it's made of plastic. It's also worth noting that cruise control on the diesel-powered Rover 75 is controlled by the engine management system in conjunction with a cruise control interface unit. There's no throttle actuator. To summarise, not only is the Rover 75 the first British car to be fitted with common rail diesel technology, but it's also the world's most powerful 2-litre common rail diesel engine available. The familiar K1.8 petrol engine, with its through-bolt construction, has been further developed to improve performance and to meet the year 2000 emission standards. It now produces 88 kilowatts of power. Engine modifications include a 5-point fixing for the right-hand engine mount to increase stiffness, an exhaust manifold incorporating a heat shield, and a starter catalytic converter. The starter cat is a lot smaller than the main cat and, as a result, warms up quickly, thus reducing emissions from a cold start. To accommodate the right-hand engine mounting and to provide the support for the starter cat, detail changes have been made to the cylinder block. A dual-mass flywheel is fitted to the manual versions. It reduces noise and improves ride comfort. There's also a new cam cover, camshafts, and Hall effect camshaft sensor. The new type of cam sensor provides a digital signal used for sequential fuel injection, and an automatic tensioner for the cam belt. It helps to reduce noise and increases the service life of the belt from 60,000 to 90,000 miles. Incidentally, to accommodate the new camshaft seals and belt tensioner, the cylinder head has been modified. The air conditioning drive belt is now fitted with an automatic tensioner, which means that, like the cam belt, it has a life expectancy of 90,000 miles. Let's now consider some of the changes that have been made to the MEMS 3 modular engine management system. We'll start with ECM's input signals. In operation, the MEMS 3 system is similar to earlier MEMS versions, but the ECM receives additional input signals concerning alternator load, power steering load, and the load of the air conditioning compressor. There's also the familiar input signal from the heated oxygen sensor. However, to meet the forthcoming ECD3 legislation, 2 oxygen sensors will need to be fitted, each providing their own input signals. One sensor will be located before the starter catalyst, and the other will be fitted just after the main catalyst. Both oxygen sensors use zirconium technology, and, like other models, the sensor in front of the starter catalyst forms part of the mixture control system. The additional sensor is part of the ECD3 system and primarily measures the efficiency of the cat. If the cat's performance is below standard, a fault is recorded in the ECM's memory. Its secondary function is to assist in the fine-tuning of the fuel and air mixture. The MAP sensor, or Manifold Absolute Pressure Sensor, which measures manifold depression, has also been relocated. Formerly located within the ECM, it can now be found on the inlet manifold, at the opposite end to the throttle plate. Next is the previously mentioned Hall effect camshaft sensor. And for the first time on a MEMS system, the ECM now receives a direct feed from the battery. In addition, the MEMS 3 system also receives information from other control units via the CAN bus. In turn, it uses the CAN bus to communicate with the rest of the vehicle systems. So, having considered the input signals, Let's now consider the new MEMS3 output signals. Firstly, there's the malfunction indicator lamp, or MIL for short. As mentioned, this is required to be active from the 1st of January 2001. This output will be active in the year 2000 on Rover 75, and it will alert the driver to problems associated with the engine management system. Other output signals supply the sequential fuel injectors, the plug-top ignition coils, and the stepper motor, which regulates the idle speed. These output devices perform the same task as previous MEMS versions, but their construction and operation are slightly different. The injectors spray a carefully targeted split stream of fuel onto the back of the inlet valves, improving idle stability and fuel economy. Two ignition units are positioned directly on top of the spark plugs, and each can be removed, allowing access to the plugs. Triggered by the ECM, one unit simultaneously supplies cylinders 1 and 4, while the other supplies cylinders 2 and 3. The ignition system is known as the wasted spark type, and is particularly compact and neat. By the way, the spark plugs have a service life of 60,000 miles. The idle speed valve is now of the bipolar stepper motor type, and primarily controls the idle speed by regulating the quantity of air bypassing the throttle body. As its motor rotates, a pintle moves, which opens or closes the idle air control valve, allowing air to bypass the throttle. The ECM can also regulate the idle speed by varying the ignition timing. Rover engineers are continually looking for ways to improve and enhance management systems. One such development is the new onboard diagnostic system contained within the engine management system and designed to meet the ECD3 legislation. MEMS3 onboard diagnostics is so refined that it can now detect engine misfires by closely monitoring the engine speed via the Hall effect crankshaft sensor. If a misfire occurs, the crankshaft speed will alter slightly, and by detecting the exact point at which the speed changed, the ECM can determine the cylinder which misfired. The ECM will store a fault code, and when active, the malfunction indicator lamp will be illuminated to inform the driver of the fault. The misfire detection facility is disabled when travelling over rough roads, as the crankshaft speed may vary due to the extreme driving conditions. The MEMS3 ECM detects these conditions by monitoring the information received from the front left wheel speed sensor via the ABS ECU. The patter or slip induced by a bumpy road surface affects the expected signal, and the ECM suspends misfire detection. Incidentally, this signal is hardwired between the ABS ECU and the engine management ECM. In this section, we'll look at the KV6 engine, which has undergone major changes to enable its transition from the Rover 800 into the Rover 75. To meet the tougher quality standards and the high expected demand for the KV6 engines, a new assembly line has been built. As a result of this major investment, nearly 90% of component parts are new, ranging from stronger main engine castings through to electrical ancillaries. The familiar KV6 from the Rover 800 formed the basis for two new engines of 2 and 2.5 litres capacity. The 2 litre was especially developed for the Rover 75. The difference between the two engines' capacities is due only to the throw of the crankshaft. The cylinder bore sizes are identical. The 2 litre engine develops 110 kilowatts of power at 6,500 RPM and a very respectable 185 Newton-meters of torque at 4,000 RPM. In its 2.5 litre version, The performance has been improved beyond that of the Rover 800, and it now produces 130 kilowatts of power at 6,500 RPM and 240 Newton meters of torque at 4,000 RPM. Let's now look at some of the engine's design details before continuing with an explanation of the new Siemens engine management system. The 90-degree cylinder block is cast in 3 sections: the cylinder block, the bearing ladder, and the lower crankcase. The new engines are more robust than their predecessors. The alloy cylinder block incorporates extra stiffening ribs and a lower tie bar to cope with the stresses inherent within the torque axis mounting system. Damp cylinder liners are used, which slide into the lower part of the block. Note that the liners are smaller than the big end forging of the conrod and therefore need to be removed complete with their piston and rod assembly. The identical cylinder heads are fitted with exhaust valves, which incorporate carbon brakes to prevent them from sticking. Also note that the new 5-layer steel head gaskets no longer include the rubber beading that featured on the earlier engines. Underneath the engine is the new sump, incorporating a baffle plate and oil cooler. A new oil pump, driven off the nose of the crankshaft, and a new oil filter complete the modifications to the lubrication system. At the front of the engine is the water pump, with its revised face and internal seals. It's driven by the primary drive belt, which also drives the inlet cams. The exhaust cams are remotely driven from the rear of each inlet camshaft. The alternator, power steering pump, and air conditioning compressor, if fitted, are driven by a new auxiliary drive belt, which is tensioned automatically. To improve belt alignment, the alternator is now mounted on a special bracket incorporating 2 split bushes. Both the cam belt and the ancillary drive belt have a service life of 90,000 miles or 6 years. The starter motor has been replaced with an uprated unit supplied by Denso. Crankcase breathing and the overall appearance of the engine has been improved by the fitting of higher volume cam covers and nylon breather pipes, which utilize neat, quick-fit connectors. The engine's appearance is also helped by the new engine cover that's designed to improve noise absorption. The remaining engine modifications are to the induction system. The inlet manifold is made from lightweight plastic and is one of the most advanced intake systems of its kind. Known as the Variable Induction System, VIS, the length of the inlet manifold is continually adjusted by several actuators and valves. The system adapts to meet changing load conditions, thereby improving the volumetric efficiency of the engine when compared to an engine with a fixed-length manifold. As a result, maximum torque is available across a wide range of engine speeds. All the components relating to the intake system are new, including the secondary throttle that works in conjunction with the optional traction control system. We explained how the secondary throttle worked in conjunction with traction control in the Rover 75 introductory video. For the cruise control system, however, a vacuum-operated linkage moves the primary throttle. Air assist injectors are located on the inside of the V. They are twin-spray targeted injectors aiming fuel onto the back of the inlet valves. A shroud of air envelops the fuel spray as it's injected, thus preventing wall wetting. The injectors fit into the 2-piece plastic fuel rail, which is part of the returnless fuel system. So let's now briefly look at the fuel supply circuit. Submerged in the tank is the fuel pump. The fuel filter is located on the opposite side, and integral to the filter housing is the pressure regulator. From the pump, fuel is delivered via a supply line to the fuel rail mounted on the engine, which, as we've seen, houses the injectors. The fuel pressure in the supply line and rail is maintained at 3.5 bar by an in-tank regulator, excess fuel simply being returned to the tank via a spill port. To complete the fuel system, a damper is fitted to the fuel rail to accommodate any slight fluctuations in fuel pressure. The spark plugs are now platinum coated, and their life has been increased from 24,000 to 60,000 miles, in line with the K1.8 engine. Both V6 engines utilize a new Siemens engine management system. As you'd expect, it's fully compliant with the forthcoming European emission regulations and includes the ECD3 onboard diagnostics facility. Apart from the additional signals to the variable inlet manifold, there are no major changes to the ECM's output signals. So let's consider the changes to the input signals and sensors, starting with the crankshaft position sender. Previously mounted on the engine, it's been repositioned to the gearbox bell housing. The sensor is now of the Hall effect type, and it provides essential information to the ECM to facilitate correct fueling and the ignition firing points. In addition to the crank sensor, there's a camshaft position sensor, located close to cylinder number 5. Like the crankshaft sensor, it too is of the Hall effect type. It produces 1 pulse per camshaft revolution and provides information for the ECM to enable sequential fuel injection. The coolant temperature sensor is now mounted between cylinders 5 and 6. Its signal is used by the ECM to vary the mixture depending upon the coolant temperature, and is also used to control the radiator fan speed and operate the temperature gauge. A TMAP sensor, or temperature and manifold absolute pressure sensor, is easily accessible. It's located on the right-hand side of the engine, just above the throttle body. As its name suggests, it's a combined sensor measuring inlet air temperature and manifold absolute pressure. The MAP part of the sensor is a piezo-resistive pressure gauge and measures the air pressure after the throttle butterfly. The ECM interprets the engine load from the MAP signal and then shares this important piece of information with other control units via the CAN bus. For example, vehicles fitted with automatic transmission use this information to reduce engine torque during gear changes to smooth the shift. The inlet air temperature signal is used in conjunction with the MAP part of the sensor to determine the quantity of air entering the engine. This information is used by the ECM as a basis for calculating the quantity of fuel required for the optimum combustion. Incidentally, if the air temperature rises to above 55 degrees centigrade, the ECM retards the ignition timing to help prevent detonation or knock. There's 1 knock sensor per cylinder bank, located on the center line of cylinders 3 and 4. If detonation occurs, the ECM identifies which cylinder has the problem and retards the ignition timing accordingly. To help meet the forthcoming ECD3 legislation, KV6 engines fitted to the Rover 75 will use 3 oxygen sensors. There's 1 in each exhaust downpipe, and the third will be located after the main catalyst. The first 2 sensors report on the exhaust's oxygen content to determine the fuel mixture preparation. The third one monitors the CAT's operation and reports to the OBD system in much the same way as that explained for the K1.8 engine. Any detected faults are stored in the ECM's fault memory and can be retrieved using testbook. So that completes our brief look at the engines fitted to the Rover 75. Thanks to their design and construction, utilizing the very latest manufacturing techniques and materials, the Rover 75's engines are truly world-class. Their design, together with their extended service intervals, has allowed Rover to set the standard for other manufacturers to follow. Above all, it's the unique combination of innovative engines and impressive vehicle design that's helped the Rover 75 put the pleasure back into motoring.